In this video, I'm going to tackle a question I've seen in a maths book, which I found quite interesting, and I think many students find difficulty solving this type of problems. This is question number 12 in exercise 21B in a book called Introducing Pure Mathematics by Smedley and Wiseman. We're basically told that in the triangle OAB, M is the midpoint of AB and N is on OB such that the ratio of ON to NB is equal to lambda to mu. And they have asked us, it's in two parts. And the first part asks us to show that the ratio of AP to PN is this expression here, lambda plus mu over lambda. The second part is similar, where they ask us to show that the ratio of OP to PM is something. Now, I haven't done the second part because once you see how the first part is done, the second part is easily calculated. Okay, the first thing we notice is that if we designate the vectors OA as A and OB as B, then we can write ON is equal to lambda over lambda plus mu times B, i.e. ON is this fraction of B. For example, if the ratio was 2 to 1, 1 would be 2/3, 1 would be 1/3. It was, say, 4 to 3, 1 would be 4/7 and 3/7. So this is why I've written ON is equal to this fraction of B. Now we observe also that the vector BA can be written as minus B plus A. How do we find that? BA is this vector going from B to A. And to go from B to A, we go minus the vector B plus the vector A. Minus B plus A, which I can write as A minus B. And therefore, BM, which we're told is half of that length, will be half times A minus B. Now, the next thing we do, we write the vector OM in terms of what we've already calculated. So OM would be B plus BM, which would be B plus BM. And with a bit of algebra, we find that OM can be written as half of A plus B. Now we need to find the length OP because P is a pivotal point in our question. OP is obviously a portion of OM. So we say it's K times OM, means it's some fraction of OM. And OM, we have already written it to be half of A plus B. Therefore, OP would be K over 2 times A plus B. We will need to use this later, so we will take a copy of it and bring it to one side. Next, using the information we already have, we need to be able to write an expression for the vector AN. Now, AN is going from A to N. I will go from A to O and then to N. So it will be minus A plus ON. Now, ON, we have previously shown it to be this quantity there. So if I have a quantity AN, then for the same reason that I worked out OP, then I say that AP will be some fraction of AN, and the fraction I call here W. So AP will be W times an, which will be w times, and I substitute an from this expression above, which is minus a plus on, and for on I also substitute from up here in red. So I'll get AP is equal to some fraction of an, which is w times our an value is there. Now that we have an and we have AP, I can write OP as minus a as, sorry, I can write OP as a plus AP, which is a plus AP, and if you follow the algebra, it shouldn't be very difficult. We get an expression for OP in terms of W here now, and we will need to use this later, so I'll take a copy of this and put it to one side. Okay, now we have here two expressions for the vector OP as shown in these two equations. Now, whenever we have a vector expressed as a linear combination of two non-parallel vectors, A and B, these are non-parallel vectors. Any linear combination of these two vectors which describes a particular vector, in this case OP, they must both be equivalent. This means that the components of A in these two expressions must be the same, and the components of B in these two expressions must be equal to each other. So we use this fact here recapped above to set up two simultaneous equations with two unknowns, because we have OP described by these two expressions, which means the coefficient of A in both OPs must be the same, and the coefficient of B in both descriptions must be the same, which gives us two simultaneous equations for the unknowns K and W, which I have rewritten here. From these two, we can write that equating the left-hand side, 1 minus W is equal to W lambda over lambda plus mu. The rest is here I've cross-multiplied, then I've expanded the brackets, and eventually with a bit of algebra we arrive at the solution that W is equal to this expression here. Using either of these two equations on the right, we can find the K is equal to this expression here. Now next, having got the expressions for W and K, we can now write the vector AP. In this case I'm using W, which is AP is, as we know, it's W times AN, and I substitute for W in this expression here, it's W times AN. The rest again is following a lot of algebra and taking like terms to find the coefficients for A and B, and we arrive at this expression for AP, and we know that Pn should be AN minus AP if I use the expressions for AN, which I have written here from our earlier slides. Then we finally arrive at an expression for Pn. Now to recap, I have an expression for AP, I have an expression for Pn. The ratio of AP to Pn must be the ratio of the coefficients of A in AP divided by the coefficient of A in Pn, and also it must be equal by the ratio of the coefficient in B in AP divided by a coefficient in B in Pn. This is two fractions that we divide, and both of them result in lambda plus mu divided by lambda, which is what we have been trying to show. If you've liked this video, please click the like button and click on subscribe. I'll see you in another video.